And today we are going to solve the problem 2.22 and 2.23 of Griffith 4th edition, Introduction to Electrodynamics. First, we will see problem 2.22, that is find the potential a distance s from an infinite long straight wire that carries a uniform line charge lambda. Com- Compute the gradient of your potential and check that it yields the correct field. So from this diagram you have this violet color a straight wire, a very long wire, infinitely long wire. Then we are taking a Gaussian surface for which this Gaussian cylindrical surface for which the radius is s. This radius is s from here to here, and this length of the cylindrical surface is L, and the charge that is line charge per unit length is lambda, and we are taking a very large distance A. So now we have to calculate from Gauss theorem. We know the surface integral E dot dA is equal to the charge enclosed over epsilon naught. This A is a small area, so if you integrate it, you will get area. Here the area is equal to uh, 2 pi s, that is circumference of this circle, Gaussian circle, surface, and multiplied by L. And what is the charge enclosed? Charge enclosed is charge per unit length multiplied by length. That is charge enclosed. Now you replace E dot this. If you integrate TA, you will get area. That is 2 pi S multiplied by L, which is equal to this lambda L over epsilon naught. Here this L and this L will get cancelled. This and this will get cancelled. Then you will get E is equal to, if you bring 2 pi s to the other side, you will get lambda over 2 pi epsilon naught s along the s cat. This indicate unit vector along the s direction, this direction. So this is your electric field. Now we have to calculate the potential. Potential by definition, V is equal to minus integral between infinite to s, that is from a larger distance to this point s. uh, E dot ti is a small length element. So now you can replace this infinite to a, because we are taking a is very large comparing this s. So we are taking infinite as a. So replacing infinite to a. Then you replace e. If you replace e, already there is a negative sign. Here you take the constant. Here constant is lambda over 2 pi epsilon naught. Lambda, of course you have negative sign, minus lambda over 2 pi epsilon naught, and I am bringing 1 over s inside the integral. I am going to integrate it with respect to s. This is our integral. So that is integral between a to s, 1 over s ts. Now we will solve this integral. Now we got the potential as minus lambda over 2 pi epsilon naught integral between 0 to a 1 over s ts. If we integrate to 1 over s, you will get natural logarithm s, and of course you have to apply the limit a s. Upper limit is s, lower limit is a. Then if you apply upper limit, natural logarithm of s minus natural logarithm of a. So this natural logarithm s minus natural logarithm a can be written as natural logarithm s over a. So your potential is minus lambda over 2 pi epsilon naught natural logarithm of S over A. Now, uh, here one problem is, if A is 0, then this natural logarithm of infinite is not defined. If A is infinite, another extreme, then natural logarithm of 0, because 1 over infinite is 0, natural logarithm of 0 also undefined. For 0 as well as infinite, this natural logarithm is undefined. So we will take the gradient of V, that is gradient of the potential. You can see this lambda over 2 pi epsilon naught. Of course, we have negative sign. A partial derivative of delta over delta S. This can be written as natural logarithm of S minus natural logarithm of A. Then if you are taking derivative with respect to S, that A is not depends on S, so this will be 0. If you differentiate the natural logarithm of x, S, you will get 1 over S. So the gradient of V is equal to minus lambda over 2 pi epsilon naught S. Now what is E? E is the negative gradient of the potential. So this negative sign will get cancelled. You will get lambda 2 pi epsilon naught S. Exactly what we got from problem 2.13. So we have validated our result. Then we will move on to next problem. And now we will solve the problem 2.23. The problem 2.23 is for the charge configuration of problem 2.15. Find the potential at the center using infinity as your reference point. That is the configuration in figure problem 2.15 is, you have a spherical cell of inner radius A and outer radius P. So now here the electric field is, let us take from the point from 0 to A. Our aim is we have to find the potential at the center, that is at the point 0 center. Then between this A to 0, what is the potential? That is inside the spherical cell, the potential is, the electric field is 0. So if R lays between 0 to A, then what about A to P? Here A to P, the charge varies with 1 over r squared. So with some constant k. So E is equal to k over epsilon naught r minus A over r squared r cat. If A is between if r is between A to P, that is if r is between this cell, between the outer cell and to the inner cell. If it is greater than P, that is outside, up to infinite, from the point reference point infinite to the point P, this electric field is k over epsilon naught P minus A over r square, if r is greater than P. So that is outside the sphere. That is from infinite to at the point outer sphere. These are the boundary condition given in problem 2.15. By definition, the V of R is equal to minus integral between 0 to R, that is potential required to bring a particle from infinite distance to a distance R, is equal to minus integral between minus infinite to r E dot dr. So what about V0, that is potential at the origin, that is potential potential at the origin V0 is equal to V of 0 is equal to first you take the value from infinite to 0 we have to calculate. So first take from infinite to point P. This is the point P, that is first integral. So minus integral between infinite to the point radius of the outer cell E dot tr. Then from this point, that is between the inner surface and outer surface. So that is between A and P is equal to minus integral P to A E dot tr. Then from the inner sphere to center, because it's center of the sphere is that is electric field at the center of the sphere is always 0, we know. So we have to integrate from A to A to 0. So A to 0 E dot tr. This will be 0 because inside the sphere the electric field is 0. So this will be 0. So there will be contribution from the first integral and second integral. So we will take the first and the second integral because third integral value is 0. Now we got that V of 0 is minus uh, integral between minus infinite to P E dot tr minus integral between P to A, that is lower limit is P, upper limit is A E dot tr. We have seen that the third integration will become 0 because inside the electric field is 0. Now you replace the E value. We know it is given in the problem the electric field outside this sphere, that is R is greater than P. P is the uh, outer sphere of the outer radius of the outer sphere. So that is equal to K epsilon naught multiplied by P minus A over R square. So now here you take constant outside minus K P minus A over epsilon naught is a constant, and you bring 1 over R squared inside the integral because you are going to integrate with respect to R. Then next integration is here between A to P, between R is between A to P, that is between inner sphere and outer sphere is K over epsilon naught R minus A over R squared. So I am replacing this E is K over epsilon naught R minus A over R squared. Now you integrate this 1 over R square. What will what you will get if you integrate 1 over R square, you will get to minus 1 over R, and you have to apply the limit infinite to P. So if you apply upper limit, you will get to minus 1 over P. If you apply the lower limit, 1 over infinite is 0. So don't worry about lower limit, only upper limit, which is equal to minus 1 over P. So you have already one negative sign here. So if you replace this integral by minus 1 over P, minus of minus will become plus. So this will become 1 over P. That is K over epsilon naught P minus A over P. Then next integral, you can separate this into two parts. One is minus K over epsilon naught r over r squared. R over r squared is 1 over r. Of course, you have tr. Next case, since a is a constant, you can take outside the integral. So Ka over epsilon naught 1 over r squared. Of course, here you have minus, here you have minus. Minus of minus will become plus. Now we have to solve the second integral. What you will get if you integrate 1 over r, 1 over r if you integrate, you will get natural logarithm of r, and you have to apply the limit between p to a. A is upper limit. So this will become natural logarithm of a minus natural logarithm of p, which can be written as natural logarithm of a by p. So that's what I have written. Then the last integral. What will happen if you integrate 1 over r squared? You will get minus 1 over r. You have to apply the limit p to a. So upper limit is a. This will become minus 1 over a upper limit, and lower limit minus 1 over p. So here you can see there is a plus sign. Here you have minus. So this will become minus Ka over epsilon naught 1 over a minus 1 over p. Now we will simplify it further. Now we got this expression. You take the last one, that is last term, this one. You take LCM a b, then the numerator will become p minus a. This p and minus a, p minus a over a b. Here you can see this a will get cancelled with this a. So this third term will become k over epsilon naught, k over epsilon naught p minus a over p. Now you compare first and third term. First term is this one, k over epsilon naught p minus a over p. Last term also same. Magnitude is same but opposite direction. So this and this will get cancelled. Finally, you will get V naught is equal to the second term allowed minus k over epsilon naught natural logarithm a over p. If you bring minus inside the natural logarithm, it will get inverse. So a over p inverse. So this minus will become plus k over epsilon naught natural logarithm of p over a, because we are taking inverse. This is the potential at the origin. Subscribe to my channel to get my latest videos, and join my channel to support its growth and enjoy the exclusive perks. Also use the thanks button to make one-time contribution and support my channel. Thank you very much.